Welcome to module number 4 from our series on constraint optimization. This module specifically addresses Lagrange duality, or how we can apply the duality principle to constraint optimization problems that we're attempting to solve via the method of Lagrange multipliers or something similar. We know that duality, we've seen in previous modules that duality or the duality principle allows us to predict the lower bound of the optimal output of an objective function f subject to some combination of equality and inequality constraints. Now, we could reformulate this to find an upper bound. Similarly, we could reformulate this to put it in terms of maximization instead of minimization problems. And we could reformulate this such that h of x is assumed to be greater than or equal to 0 as opposed to less than or equal to 0. But we're not going to look at all these different cases because frankly it's just going to make this module more complicated. So we are going to assume, at least for now, that we're dealing with minimization problems, h of x being less than or equal to 0, and consequently we're looking for a lower bound when we apply duality. Now, to understand duality, or at least understand it better as it applies to optimization, we must clarify the following question. What is our mathematical objective when applying the method of Lagrange multipliers to our Lagrange function? Now, it's not to minimize the Lagrange function with respect to x, lambda, and mu, which is perhaps what some people may have assumed from what we discussed in modules 1 through 3. It is the search for extrema, more accurately, and this requires both maximization and minimization, as we'll see in a moment. So let's consider the constrained optimization problem defined below, as well as its associated Lagrange function. So we're trying to minimize an objective function with respect to x. Now, this just simply tells us in what space our x resides. And then we have our equality and our inequality constraints. Again, I apologize. I don't know why these notes keep getting overwritten by the brackets. Now, for any feasible state, we can define our Lagrange function as shown below, and that's all that x sub f really means. It just says it's a feasible solution, which is not necessarily optimal, but it does satisfy both g of x is equal to 0 and h of x is less than or equal to 0. So feasibility is defined by our g and h set of functions. So the Lagrange function, this is nothing new here. We formulated this many times. Our Lagrange function is the sum of the objective function plus lambda times the equality constraint, plus mu times the inequality constraint, where both lambda and mu represent our dual variables or our Lagrange multipliers, and x represents our primal decision variable set. Now, we should note that complementary slackness applies to optimal solutions only. Hopefully, you remember from our module on the Kruskal-Tucker conditions on KKT what complementary slackness refers to. It tells us that for any optimal solution, the product of mu sub OPT, so an optimal mu Lagrange multiplier, times h of x sub OPT, so the optimal system state supplied to our inequality constraint, the product of both of those equals 0. And k is just telling us which constraint and its associated Lagrange multiplier we're talking about. So for all the inequality constraints, the product of its inequality, of its Lagrange multiplier, and the value it generates should be equal to 0. So this statement up above does not hold for a simply feasible solution. However, both of the following statements below do hold for feasible system states. Again, x sub f. What we know is that all of our mu Lagrange multipliers must be greater than or equal to 0. This is part of our dual feasibility assumption or condition from KKT. And h of x sub f is less than or equal to 0, and that's part of our primal feasibility condition. Okay, so what we observe is that for any feasible solution, the product of these two, okay, as shown down below, should be less than or equal to 0, because what we have is something that's positive times something that is negative. And so we end up with a value that's less than 0. However, because both of these can also be 0 in and of themselves, we end up with less than or equal to 0. Okay, so this right here is an important observation, because if the product of mu and h for any feasible solution is less than or equal to 0, that means that the value of the Lagrange function is always less than or equal to the value of its associated objective function for any feasible solution x sub f. In other words, we observe that the Lagrange function, when we feed it these feasible values, always provides a lower bound on what the objective function could be. Now, what about infeasible values? Generally, the lower bound would be positive or negative infinity, but we're not going to spend too much time discussing those. This equation will probably do a better job of explaining what we said at the very bottom of the previous slide. Okay, so here we have our Lagrange function, right? And it is defined in terms, or it's fed, feasible values, x sub f lambda sub f, and mu sub f. Okay, and what we have is our objective function. We have the product of lambda and the equality constraints, and we have the product of mu and the inequality constraints. Now, what is the value of this right here for any feasible solution? It should always be equal to 0, right? Because for any feasible state, g of x must be equal to 0, and so this whole thing would be equal to 0. And what we end up with is f of x plus mu h of x. Previously, we observed that this was less than or equal to 0. So what we have is f of xf plus something that we know is less than or equal to 0 will always be less than or equal to x f of x sub f, right? This is a pretty simple logical relationship or mathematical relationship. If we take a value and we add to it something that is negative, that the combination of the sum of those two will be less than the value itself. All right, so this is merely a lower bound on x sub f. What if we want more than a lower bound of that? What we can do is we can maximize the Lagrange function with respect to lambda and mu. This pushes that lower bound L as high as possible, as close as possible to the actual value. So if we look back here, what we're talking about is taking this lower bound of x, f of x, and trying to push that as high as possible to get it as close as we can to being equal. And in order to do that, we must maximize with respect to mu and lambda. So we observe that both minimization and maximization are used to find the extrema, right? Minimization with respect to x and maximization with respect to lambda and mu. And that was really not explicitly stated in module number 1. We kind of sidestepped that issue, talked about finding extrema and taking the gradient of the Lagrange function with respect to both primal and dual variables, setting them all equal to 0, which may have led some people to assume we were looking for a minimum when that wasn't what we were doing. All right, and so here we see a mathematical representation of what we're talking about. What we see is that if we maximize our Lagrange function with respect to lambda and mu, with the assumption, still dual feasibility applies, mu must be greater than or equal to 0, we will end up with a value that is equal to the objective function itself, assuming that x is feasible. Now, if it's unfeasible, then we can end up with positive or negative infinity, but we're really not too concerned with that at the moment. So what we see is that we can use the Lagrange function to approximate the objective function for some feasible state, x sub f, if we maximize the Lagrange function with respect to mu and lambda. So we had a lower bound on f of x, and we're trying to maximize the lower bound, which then would push the two up against one another. So we know that the Lagrange function, if it supplied feasible inputs, defines a lower bound on f of x sub f. Okay, and remember, this only works for the same input. So we haven't applied duality yet explicitly. These two values must be the same. The Lagrange function provides a lower bound on the objective function, assuming that the same inputs are being supplied. We also observe that by maximizing the Lagrange function with respect to the Lagrange multipliers, we may yield, and not, well, optimal solution is a bit misleading here. I'm going to say we may yield the actual value of f of x sub f, or at least a lower bound on f of x sub f. So, if we combine a couple of these assumptions together, what we see is that if we want to minimize the objective function, which is generally what our goal is for these constraint optimization problems, that may be equivalent to minimizing the maximum of the Lagrange function. And I'm going to explain that in 1 second in a little bit more detail. Note that this, in some regards, represents a rederivation of the method of Lagrange multipliers we presented previously, but perhaps a little bit more accurate. Now, we still have not addressed duality yet. And the order of these operations, we'll see in a second, is important, the maximization and the minimization. Previously, we really just assumed that we were doing them in parallel. So I want to talk about this relationship between the Lagrange function and f in a little bit more detail just for 1 second. So let's try to use some math to restate what we said on the previous slide and perhaps clarify a couple points. So going back to the very beginning, right, we start off with an objective function we call x of f. f of x. And we're going to assume that a feasible state is being fed to that objective function, where the feasible state, right, is that for which, right, the feasible state is defined by those two constraints. Okay. Now, what we saw, I'm going to leave myself some room here, is that the Lagrange function is less than or equal to the value generated by the objective function, assuming that, again, some feasible state is being fed to it. Now, what if we want more than a lower bound on f of x? We can try maximizing the Lagrange function with respect to mu and lambda. And in some cases, what that can do is it can transform our inequality into an equality. Right? What we've done is we've taken our lower bound and pushed that up high enough such that it touches the actual value and changes our inequality to an equality. So we have a very good approximation and equality, an equal, to f of x over here. But that's not generally the objective of these constrained optimization problems, right? Generally, the objective is to minimize, with respect to x, our f of x. Okay, so if we apply this to the right-hand side, can't we just apply the same thing to the left-hand side? Right, if we assume that all of this right here is equivalent to f of x sub f, then we can just minimize it in the same way we did on the right-hand side. And so this equation is one that's going to come in very handy later on in this module. Essentially, not to be repetitive, but this idea that it's equivalent to minimizing our objective function with respect to x. And we know we're adhering to these constraints because we're only considering feasible solutions or feasible states, right? All of this is equal to maximizing the Lagrange function with respect to mu and lambda, and then taking this output and minimizing that with respect to x. And so this slide restates what we said a second ago. All right, if we're trying to approximate the minimum of the objective function with respect to x, which we can call f of x sub opt, or the objective function when we have an optimal value supplied to it, okay, that is equal to taking our Lagrange function, maximizing it with respect to lambda and mu, and minimizing it with respect to x. And again, we're not going to talk anymore about flipping maximization and minimization. Now, the one thing I should point out here is that, as I said a couple of slides back, order is important, right? We cannot simply switch the order of the minimization and maximization without affecting this relationship, okay? And that's the next topic, or the next aspect of this that we're going to focus on. All right, so to reiterate for 1 second, to minimize our objective function x, we need to perform two different operations, okay? We need to maximize our Lagrange function with respect to mu and lambda. All right, the Lagrange function is inherently affine, okay? Or affine is simply just a linear function with some offset, okay? It's affine with respect to the dual variables, or the Lagrange multipliers, lambda and mu. An affine function is both simultaneously convex and concave, and as such, we know that the maximum of the Lagrange function yields a global maximum because the function is concave, or both concave and convex at the same time. So the nice thing is, we do expect for this maximization of the Lagrange function with respect to lambda and mu to yield a global maximum. Next, we need to minimize the Lagrange function with respect to the primal variable x. And perhaps it would be more appropriate in here to say we need to minimize the maximum of the Lagrange function. But I think you understand what I'm trying to say. Now, with respect to the primal variable x, this Lagrange function may be nonlinear. Okay, and so we cannot necessarily assume that the Lagrange function is convex, as would be required for minimization, or to generate a global solution if we're applying minimization. Okay, that would require the assumption that both the objective function as well as all the constraints are convex. So we can't necessarily assume that we'll be able to generate a global solution with respect to x, although generally we will be able to, and we'll kind of employ some pseudo-assumptions with respect to that. Now, ideally, we can perform these two steps, 1 and 2, in order. Or as we did in module number 1, 2, 3, really we did them in parallel with one another. But it's not always feasible or practical to perform these two steps in order. Is there an alternative? And this is where we get to the duality principle. Really, it brings us back to the question, of can we flip the order in which the minimization and the maximization are applied to the Lagrange function. In order to answer that, we need to employ the duality principle. All right, so we've already investigated how to apply primal optimization or traditional optimization, right? This minimizes a maximized equivalent to f of x. And you can see that on the right-hand side here, on the left-hand side here. Okay, again, what we do is we maximize the Lagrange function with respect to mu and lambda, which gives us a good approximation of f of x, and then we simply apply the minimization to that to give us the optimal solution. Okay, but on the previous slide we asked the question, what if we can't do this? What if we can't use this order? Dual optimization maximizes the lower bound of x of OPT. It generates a lower bound. It requires us to switch the order of the maximization and the minimization as shown below, or perhaps more accurately allows us to switch the order. And unless strong duality applies, which we talked about duality in the last module, this would be merely a lower bound on f of x OPT. All right, but before we move on, let's compare the equation on the left and the right-hand side. So really the only difference is, and you can see I tried to use yellow and blue to demonstrate we switched the order. On the left-hand side, we first apply maximization, and then we minimize the maximized value, right? We are maximizing the Lagrange function to generate f of x, or an equivalent to f of x, and then we're minimizing that. For dual optimization, we're doing the opposite. We're minimizing the Lagrange function with respect to x, and then maximizing that value with respect to lambda and mu. And this doesn't use the same set of assumptions we had over here to the left. So primal optimization generally is solved in one step, right? As we saw in the first three modules, generally we do both the maximization and the minimization in parallel, whereas for the dual optimization, we generally don't use it unless we plan to solve the two steps serially, one after the other. Now, why is this greater than or equal to and not just equal? Why do we have to add the greater than symbol? Or why is there some inequality aspect to this relationship when we flip the order of the minimization and maximization? And this inequality is a side effect of the min-max inequality that applies to any similar function. And so, I mean, you can really just Google this term and you can take a look at the min-max inequality. But it explains why we have to replace the equal sign with greater than or equal to. Again, please still keep an eye out for these QR codes in the top right-hand corner. They they provide references that I used when I was generating these lectures. All right. So motivation for the dual approach, because some of you may be asking, well, what's really the big deal here? We're just flipping the order in which we apply the minimization and maximization. Is there really any advantage to doing this? Now, there are some advantages, some motivations we can outline. One has to do with the problem structure. So the forms of f of x, g of x, and h of x may make it difficult to perform maximization and then minimization, or to do these two in parallel, as is required for the primal method or the traditional method. As such, solving the primal problem may be infeasible or impractical, and we apply the dual approach as an alternative. It can also help us reduce the dimensionality of the problem. So for complex problems, the number of primal constraints, right, and that would be g of x and h of x, is generally less than the number of primal variables, right? x1, x2, ... And so as such, solving for the optimal array of the dual variables of the Lagrange multipliers may be easier than solving for x. Okay, remember that the number of Lagrange multipliers is same as the number of constraints. So if we have fewer constraints, then we do primal decision variables. We also have fewer Lagrange multipliers, then we have primal decision variables. And so if duality allows us to solve for lambda and mu first, as opposed to these x values, if these values have a smaller number, it may be advantageous to try to solve for those first. Okay, so we may see that solving for the optimal array of the Lagrange multipliers may be easier than solving for the optimal x. Now we are going to go through a step-by-step example of how to apply duality. So if this isn't clicking 100%, that's okay. You'll have an opportunity to see it in action. Now, another motivation is that the dual approach may be optimal for certain applications. Some applications, for example, transportation problems, have dual forms which facilitate the use of better, existing strategies. For example, a complex transportation problem may translate to a shortest path problem. And then another example of a potential motivation would be the potential for economic interpretations. So as we are going to discuss in the very last module, we're actually going to dive into this one pretty deeply. The dual form may allow us to reinterpret a resource allocation problem as a resource valuation problem and discuss topics such as shadow pricing. Now, I could talk about that in a little bit more detail here, but again, since we have another module that's discussing that topic explicitly or specifically, I feel like we can just wait till then. All right, so what is the dual Lagrange function? We know what the traditional or the primal Lagrange function is, and now we're going to introduce a new version of that, which we call the dual Lagrange function. So when we minimize the primal Lagrange function with respect to x, we simply call that the dual Lagrange function. So if you see down here, right, we have the original, the traditional, the primal Lagrange function, and we've minimized it with respect to x, and so that gives us our dual Lagrange function. And then that is what we are going to try to maximize with respect to lambda and mu. Now, what are some characteristics of this dual Lagrange function? It should not be a function of primal variables, right? We hope that if we do this correctly, our x will go away. And that's going to make it much easier to do this maximization. So after minimization with respect to x, this function should be defined in terms of the dual variables only. And that's why you can see up here, we've left out the x. It should also be concave with respect to lambda and mu. The dual function is the pointwise minimum, or infimum, of an affine function with respect to the dual variables lambda and mu, and as such, it is always both concave and convex. We talked about this a second ago, and all we need is for it to be concave, and so that's positive. That's what we want. So fortunately, this concavity is independent of the convexity of either f of x or L or the Lagrange function with respect to x. So what is that saying? That we know the Lagrange function will be concave with respect to lambda and mu, and that has nothing to do with the characteristic of that function with respect to x. All right, so let's take a look at an example, and let's see how we can apply the duality principle here. I'm going to try to break this down into very granular steps, so hopefully we can understand better some of that language from the last couple minutes. Okay, so pretty straightforward constraint optimization problem here. We have an objective, which is to minimize this function with respect to x. It's simply x1 squared plus x2 squared. I feel like a broken record. I keep saying that, for these rank 1 arrays, generally the superscript or the subscript, right, they mean the same thing. We use both of those to just simply indicate which element of the array we're speaking about. Okay, we also, for this example, have an equality constraint, which simply just says that the sum of those two together should be equal to 1. And then we have an inequality constraint, which says that x1 must be greater than or equal to 0, which is the same as saying negative x1 must be less than or equal to 0. And that's what we have written over here. Now you can see that these are both the equality and the inequality constraints do have a linear form. And so we could imagine this as having a coefficient ag1 is equal to 1, a coefficient ag2 is equal to 1. We could imagine this as bg, and then do the same thing and put this expression in terms of AH. But we'll come back to that a little bit later. And if you're familiar with linear systems, you'll be aware of the ability to implement it in that way. All right. Now, just to provide an ideal solution, a preview, what I did was I went ahead and solved this problem via MATLAB, using MATLAB. I'm not going to go through the code step by step because I think we've done several examples like this. But anyway, we can see here that MATLAB tells us that the ideal solution is x1 is equal to 0.5, x2 is equal to 0.5. All right, great. So now, as we try to solve this problem using duality, we know what the ideal solution is that we're looking for, and also the output of the objective function for the optimal value will be 0.5. All right, so we know that the optimal x 1 and 2 are 0.5 and 0.5, and in the same regard, the minimal value of the objective function is also 0.5, and that's just a coincidence. Well, it's not a coincidence that they're the same value, but that's the way the math worked out. Now, if you are looking at this MATLAB code in more detail, you will see that we did use the z variable, the one that we introduced in module number 3, in order to convert the inequality constraint to an equality constraint, and then we plugged all that into MATLAB. You can see right here, we converted our inequality constraint to an equality constraint by essentially saying z squared minus or plus h of x equals 0. Again, this should all look familiar if you go back to module number 3. All right, so let's outline the specific steps required to apply duality to this example. First step is to minimize the Lagrange function with respect to the primal variables x. Now, like we said, the first step in the dual approach is to minimize the Lagrange function with respect to the primal variable x. How is this done? Now, one approach, and this is going to remind us of the traditional or the primal approach, is to calculate the gradient of the Lagrange with respect to x, not x and lambda and mu, only x, and set that equal to 0. Now, how do we know that this is a minimum and not a maximum? This goes back to the convex question we asked earlier. If the extrema that we calculate from here is a maximum, then that would mean that the objective function is concave. And this seems, pretty counterintuitive if the original goal was to find the minimal output of the objective function. So we're really going to use a common sense approach here, which assumes if we're asked to do minimization, most likely it's being applied to a problem where we have a convex or at least affine objective function in order to make sense and be something that's a valuable goal to achieve. All right, so down here, again, we're just demonstrating that part of this first step is to differentiate the Lagrange function with respect to x. And I think we've already shown what the Lagrange function was for this example, but I can show it one more time. As usual, it's going to be the sum of f of x, which is x1 squared plus x2 squared, plus lambda times the equality constraint, which is x1 plus x2 minus 1 equals 0, plus mu1, that Lagrange multiplier, times the inequality constraint, where this is simply just saying that x1 should be greater than or equal to 0, and this gradient should be equal to 0. So we use this in order to minimize L with respect to x. Okay, so here we can see the actual math. Again, we have our original Lagrange function, and we differentiate it with respect to x1 and x2. I can quickly go through this, but I'm hoping that everyone watching kind of understands this process, right? x1 squared gives us 2 times x1. Okay, this doesn't have any effect on the first gradient. Then we have the derivative of x1 lambda 1, which leaves us with lambda 1. Okay, these two don't affect the first half of the gradient. And then we have negative mu1, right, because the x1 will go away. Then if we take the gradient with respect to x2, we end up with 2x2. Okay, then we have plus lambda 1, again, because we see here we have the product of x2 and lambda 1. This would go away. This doesn't have any effect on the second gradient, and this doesn't have any effect on the second gradient as well, which is why we don't have a third term. And we can solve these two expressions to define what I'm going to call x min L, or the x values that minimize the Lagrangian, and they'll be defined in terms of mu and lambda. So here we see that the x value, x1, that minimizes Lagrangian is equal to 1/2 mu1 minus 1/2 lambda 1, and the second x value that minimizes Lagrangian is negative 1/2 lambda 1. Okay, step number 2. We need to define the dual Lagrange function. If you remember, right, the dual Lagrange function is simply just equal to the primal Lagrange function minimized with respect to x, or that could be the same as substituting in our x min of L, or min L. Okay, so we substitute x min L into the primal Lagrange function to generate the dual Lagrange function, which is shown below. And as we said previously, this new function should not be dependent on the primal decision variable x, okay, because it was already minimized with respect to that value. And so what we end up with, and you can see in here, I substituted in for x1 min L. Here I substituted in x2 min L, x1, x2, and then x1. Okay, so all I did was take the Lagrange function, the primal Lagrange function shown here, and then take this value, substituted in here, substituted in here, substituted in here, then take this value, substituted in here, substituted in here, and essentially after we do those substitutions, we end up with this function right here. Now, here and here, all I did was just combine some of the terms together. If you're interested in the algebra, you can take a closer look yourself. I used the red to identify the terms associated with mu1 squared. I used the green for lambda 1 squared. I used the blue for the terms that are associated with the product of mu1 and lambda 1. And the purple is just lambda 1 by itself. Anyway, when you combine all these terms together and simplify, you end up with a dual Lagrange function that's equal to negative 1/2 lambda 1 squared, positive 1/2 lambda 1 mu1, negative 1/4 mu1 squared, minus lambda 1. Okay, so this is our dual Lagrange function, which represents the primal Lagrange function minimized with respect to x, and so now our x falls away. All right, and MATLAB can help with these substitutions. This MATLAB code right here, this script, which I'm not going to go through in detail, you can use that in order to help you with some of these substitutions and some of the simplification that we performed here. All right, so next step. Okay, we need to maximize the dual Lagrange function with respect to mu and lambda, but we also have a problem with inequality. So we can't forget to apply our KKT conditions, and specifically, we're going to have to make an assumption with regard to complementary slackness. So we may have to redo this. In fact, we will have to perform this step number 3 2 times. Let's start off with the assumption that h of x is equal to 0. So hopefully you remember that there's 2 types of assumptions for a given inequality constraint when it comes to complementary slackness, right? We can either assume that h of x is equal to 0, which means that the constraint is binding, or we can assume that h of x is less than or equal to 0, and that its associated mu value is equal to 0, and this would be the case when it's non-binding. And so we are going to have to end up looking at that. But let's start off with the binding case. All right. So step number 4. So step number 3 was to make that assumption. Step number 4 is to maximize the dual Lagrange function with respect to lambda and mu. And we're going to employ the complementary slackness assumption that mu1 is greater than or equal to 0, and at the same time h of x is equal to 0. Or here I wrote the same thing. H of x is equal to 0. All right, so here we have our original dual Lagrange function, just what we generated from 2 slides back. But we can create a new version with the KKT conditions applied. In this case, we don't change anything because we're not assuming that mu is equal to 0, so we can't change anything. So essentially, our original dual Lagrange function is the same as the dual Lagrange function after we apply the KKT assumptions. But you can kind of see, if you look forward a little bit, you can see that when we change the assumption and we move to lambda 1 is equal to 0, right, then we can eliminate some of these terms. Okay, so we have the same dual Lagrange function. The second step, or the second part of step number 4, we're still trying to maximize the dual Lagrange function. We can calculate the gradient of the dual Lagrange function with respect to lambda and mu. Right, again, we're using this dual Lagrange function or the derivative of it, the gradient of it, to calculate the extrema and set those extrema equal to 0. And so then we're going to define an equation that is going to allow us to solve for these 2 values. And actually, I apologize, this should be mu, right? Because we're solving for both lambda and mu. Now, what does this subscript mean? Lambda max dual is just the value that maximizes the dual Lagrange function, and mu max dual is, again, the mu value that maximizes the dual Lagrange function. Okay, so here, again, we have our dual Lagrange function, and we calculate 2 different gradients, right? Because we have 2 Lagrange multipliers with respect to lambda, with respect to mu. Okay, with respect to lambda, right, we take this 2 and bring it over here, so we end up with negative 1 lambda. This term, right, this will go away, so we end up with positive 0.5. This term will go away because we're differentiating with respect to lambda. So we end up with 0.5 mu1. And then this term will go away, leaving us with just a minus 1. Then we differentiate the same thing with respect to mu. This term doesn't have any effect. This term will go away right here, leaving us with 0.5 lambda 1. This 2, right, when we differentiate, will come out as a coefficient in front of the 0.25. And so we end up with 0.5 or negative 0.5 mu1. And then this doesn't have any effect on the second gradient, or the second part of the gradient. Now, if you take a look at these 2 equations, you can see they may be formulated as such, right? We have negative 1 times lambda plus 0.5 times mu equals 1. We have 0.5 times lambda minus 0.5 times mu equals 0. And so we can solve this, and that's what we're going to do on the next slide. All right, so we're going to solve for lambda max dual and mu max dual. I just went ahead and typed this into MATLAB and solved. Right, I just inverted this matrix and multiplied by this array over here. And what we end up with are 2 values that are the same. So lambda and mu that maximize the dual Lagrange function, both of them are negative 2. And this is a problem because it violates dual feasibility, right? Dual feasibility tells us that all the mu values must be greater than or equal to 0. So we could really stop right here and not continue any further because this is not a viable solution. However, I did kind of finish this out just as a preview for what we're going to do next time. We can substitute these values in and calculate x values, but in the end, this is really not a viable solution. And if we check the primal feasibility actually works out. it's the dual feasibility that doesn't work out, because again, we end up with a mu value that's less than or equal to 0. So dual feasibility was violated because of this. So the last step is always to check primal and dual feasibility, although oftentimes, like what we just saw for this example, you can check it earlier and then just kind of bail on that given assumption. So we know that our first assumption was not correct, was not feasible. So now we're going to flip it. We're going to assume that h of x is less than or equal to 0. It's non-binding. Okay, and in order to maintain complementary slackness, mu must be equal to 0. So we have to restart from step 3 and reperform the same step 4, step 5, and step 6. Okay, so again, we're going to maximize the dual Lagrange function with respect to lambda and mu. We're going to employ complementary slackness, but this time with a different assumption. And again, right, we assume this constraint was non-binding, so h of x is less than or equal to 0. Now, unlike the previous case where the original dual Lagrange function before and after we applied the KKT assumptions was unchanged, in this case it will be changed, right? Because everywhere we see a mu1, we're assuming that's equal to 0. So this goes away, and you end up with this and this. You end up with a dual Lagrange function that is only defined in terms of lambda. Okay, now pretty much the same process. We still want to maximize the Lagrange function with respect to lambda. We don't have to do it with respect to mu because we know mu is equal to 0. So again, we're going to calculate the gradient, the derivative of the dual Lagrange function with respect to lambda, and set it equal to 0, and then solve for lambda. All right, so this was our original dual Lagrange function. We don't really need that at the current moment. This is the dual Lagrange function with the KKT assumptions. Okay, and so what we have to do is just simply differentiate this function with respect to lambda, and so we end up with the 2 coming over here, so we have -1 lambda 1, and then anytime you take the derivative of lambda with respect to lambda, you end up with a 1, and so that leaves you with a -1 over here. So what we end up with is -1 lambda minus 1 equals 0, and we can solve that pretty easily and determine that lambda max dual, okay, right, the lambda value that maximizes the dual Lagrange function is equal to -1, and the mu is equal to 0 because that was part of our KKT assumption associated with complementary slackness. All right. And so now, continuing with step number 4, we have step 4c. We can substitute these two values into our previous expressions for the x min L, or the x values that minimize the primal Lagrange function, in order to solve for the optimal solution x OPT, which actually I more appropriately call dual OPT. Because, right, this solution is not necessarily equal to the optimal solution we would get if we solved it traditionally. And the reason for that is because, right, I'm running out of space here, I apologize. So the reason why these two values are not equal is because, again, duality simply tells us that this sets a lower bound on this. So the values are not necessarily the same. Anyway, so we substitute this and this into the expression we yielded from step number 2, and we end up with the dual optimal values as 0.5 and 0.5, which we already saw when we used MATLAB to solve this to get the ideal solution, but that is the correct solution. So we know that strong duality is going to apply. The answer that the dual approach yields is the same as the primal approach. Now we can't forget to check all of our constraints, to check both for primal and dual feasibility. So dual feasibility we don't really have to worry about because we assume that mu was equal to 0, which by default satisfies the dual feasibility condition. We do still have to check primal feasibility, so we take these values, we add them together, -1 equals 0, right? So that satisfies the equality constraint. And then the inequality constraint tells us that the x1 value should be greater than or equal to 0, or the negative of it should be less than or equal to 0. And that fits because x1 is equal to 0.5. And step 6, we can define the lower bound. This is essentially just plugging in our optimal, our dual optimal values into this. And so this is simply the objective function. And so what we end up with is this inequality. We know that 0.5 is less than or equal to whatever the optimal value, the optimal solution to our constrained optimization problem is, which we already used MATLAB. We saw it was 0.5, so strong duality applies. Right? Again, strong duality is simply the case where the duality gap, the difference between this and this, is equal to 0. So I do provide MATLAB code which allows you to solve this problem using the dual approach. This module is already getting pretty long, and we have done several other MATLAB demos line by line where I opened it up in MATLAB and explained each command within the script step by step. So I think we're going to skip that process when it comes to this module. I think most of these commands within this MATLAB script should seem familiar when you go back and look at what we did in modules 1, 2, 3, the previous modules. So you can find the MATLAB code using this QR code here. I'll make it a little bit bigger in case you can't see it as small as it was before. Anyway, you can use this QR code to download the MATLAB script, and if you have questions, go ahead and throw those in the comments. Okay, so let's compare the primal and the dual optimization processes, the methods, and sort of try to compare and contrast them step by step. So for primal optimization, right, what we do is we start off by defining the gradient of the Lagrangian with respect to x, and this defines the stationarity KKT condition, right? Whereas let's just assume here that we have both equality and inequality constraints. Okay, so this serves as the stationarity KKT condition. Then we have to apply our complementary slackness assumption, one of these two, okay, and this applies to every inequality constraint. So if we have more than one, right, we'll have 2 to the n number of assumptions to make. Right? We have 2 cases for every inequality, and so therefore the number of cases that you have to look at increases 2 to the n. So for each inequality constraint, you need to assume that either it's binding, and that hk of x is equal to 0, or it's non-binding, where its associated mu value is equal to 0. Then step number 3 is to define the remaining KKT conditions. This includes the primal and dual feasibilities, as well as the complementary slackness, including those assumptions from step number 2. Then we use linear algebra or some sort of nonlinear analysis to solve for all the variables. And this is where, if we wanted to really follow strictly the process that we defined here, we would perform the maximization with respect to lambda and mu first, and then do the minimization with respect to x second. But again, generally, we can do all that together in parallel in one step. Then we have to check for primal and dual feasibility to make sure that they're satisfied, and then we can determine what the optimal output of the objective function is. Now, dual feasibility works a little bit differently. Okay, we start off by minimizing the Lagrange function with respect to the primal variables x. Then we define our dual Lagrange function, okay, which is equal to the primal Lagrange function minimized with respect to x, and this should remove x from this expression. Step number 3, which is similar to step number 2 over here. We apply the complementary slackness assumption. Again, we either assume it's non-binding or it's binding. We plug that into our dual Lagrange function, and then we maximize it with respect to lambda and mu. We check the primal and dual feasibility constraints that come from KKT, and then we define the lower bound of the output of the objective function by simply taking that optimal x dual OPT value and plugging it into the objective function. Now, I did also solve this using the traditional method, so what we did in module number 3, I guess. So I'm going to quickly go through that just to show that it yields the same solution, but I'm not going to go through it in as much detail, again, because this module is also already getting pretty long. We've gone through this once before. Okay, so using the traditional method, right, we have our original Lagrange function. We're still dealing with the same example, same objective function, same equality constraint, same inequality constraint. We differentiate it with respect to x. We get the same gradients. Okay, now we have to apply our complementary slackness assumption. We start off by assuming the constraint is binding. And so here we have our KKT assumptions or conditions listed out. Stationarity, which comes from the gradient. Primal feasibility, which comes from the constraints. And dual feasibility, which comes from our complementary slackness assumption. Now really the only change we make here is we assume that h of x is equal to 0 because, right, that is the assumption we're making. And now, from this point forward, we're just going to use algebra to solve these expressions together. So we substituted in x1 equals 0 into this first gradient up here, and we can then use g of x in order to solve for x2. Sorry, we substituted in here as well as down here. So we actually are going to use this expression in order to solve for x2, because we have x2 minus 1 equals 0, and that's the same as x2 equals 1. 1 minus 1 equals 0. So now we have values for both x1 and x2, which we can plug in up above. Step 4b, substitute in our known x values. So this, I apologize, is when I was using coefficients instead of the actual value. So this is equal to plus 1 divided by plus 1, which equals 1. Anyway, so we take these values. You can see we plug them in here. So we end up with 2 times 0 plus lambda minus mu. Okay, and then we would plug in here a value of 1. So we would end up with 1 plus lambda 1 equals 0. Okay, and so that's what we end up with. So our x1 went away. Okay, so we end up with lambda minus mu equals 0. We end up with 2 plus lambda equals 0. And so we use the second expression, this one right here, in order to generate our value of lambda, right? So if 2 plus lambda equals 0, that's the same as saying lambda equals negative 2. And then, right, we could plug this in here to the first stationarity condition in order to get a value of mu1. So we take this value of lambda, plug it in up here. We end up with negative 2 minus mu1 equals 0, or mu1 is equal to negative 2. Okay. And now we have all 4 of our variables, right? We have x1, x2, mu, and lambda. And we check for feasibility. Unfortunately, for this case, dual feasibility is not satisfied because negative 2 is not less than or equal to 0. So this case doesn't work. I'll go really quickly through this last step because this has already gotten pretty long. So now we redefine our assumption. Instead of assuming that h of x is equal to 0, I don't know why the pen color changed here. Instead of assuming that h of x is equal to 0, okay, which that assumption did not work, now we take the complementary, as the name suggests, right, the complementary assumption, which states that mu1 is equal to 0. All right. Now, with that assumption, we follow a pretty similar process. There's a mistake here. This should be mu1. I don't know why that's a 1. Anyway, so we have our stationarity, our primal feasibility, and our dual feasibility KKT conditions. The gradient of the Lagrange function with respect to x, that doesn't change. So it's the same one we used from the case where we assumed h of x was equal to 0. The primal feasibility also stays the same. The only exception is, right, this is no longer equal to 0 because we're not assuming that it's binding. And then the dual feasibility, or the complementary slackness condition, does change because we know that mu1 equals 0. So this up here would be equal to 0. So what do we have to do? Again, use linear algebra in order to solve. We know that mu1 equals 0. So we substitute in a 0 right there. That leaves us with 2 linear algebraic expressions in terms of 2 variables. Actually, no, it doesn't. I apologize. It's 3 variables, but we can still solve for x1 and x2 in terms of lambda. So we end up with x1 is equal to negative 0.5 lambda, x2 is equal to negative 0.5 lambda. So we know that those values will be equal to one another, x1 and x2. Next, we can substitute those values into g of x. So not to be repetitive, but a lot of this is just applying your algebra skills. Okay, so we end up with g of x. We substitute in our x1 and x2 values here, and ultimately, if we flip forward, we see that that leaves us with just negative lambda minus 1 equals 0. And so we can solve for lambda 1 is equal to negative 1. We can then substitute those values in up here. Again, we end up with the same value. So negative 0.5 times negative 1 gives us positive 0.5 for both. Now we need to check all of our primal and dual feasibility conditions. Dual feasibility is not really a problem because we assume that mu was equal to 0, so it is by default greater than or equal to 0. We do have to check our h of x constraint, and fortunately it does apply, it is satisfied, because minus 1 times positive 0.5 is less than or equal to 0. If we wanted to, we could go ahead and check the g of x constraint again, but we use that in order to solve, so we can assume that that is satisfied. And so this demonstrates how to solve that same example using the primal approach and the KKT conditions. We end up with the same solution that was yielded by the dual approach, which is, number one, a good thing because it shows agreement between those 2 methods, but it also, again, tells us that strong duality applies here, right? Because both the primal and the dual approaches yield the same solution, and that the duality gap is equal to 0. So, quick summary here. I know this has already been pretty long, so I don't want to spend too much more time on this. But Lagrange duality, right, requires us to reverse the order in which the minimization with respect to x and maximization with respect to mu and lambda is applied. Okay, we went through, we derived all that, we showed how that was implemented. Now we know that when we reverse that order, the resultant Lagrange, or the resultant process, yields a lower bound on the optimal value of f. Right? So when we apply the dual approach, we end up with x dual optimal or dually optimal. We feed that to our objective function, and whatever that supplies, that generates, that yields a lower bound on what the objective function would generate if we had the true ideal optimal solution. Now, in the case like this one, where strong duality applies, these two are equal to one another. And the duality gap is simply one minus the other. So if we compare the primal or traditional and dual approaches, there's some questions that arise. I mean, they did seem pretty similar. They do rely on similar principles and equations. So what's the point of doing this? I mean, really, to understand the value, you'd have to dive into more complex and nonlinear problems. They would better demonstrate the difference between these two approaches, and that's something I hope to get to in a future lecture. My goal in this lecture, in this module, was really just to explain what the duality concept is, highlight a couple of main characteristics, and demonstrate how you can apply the duality approach to a pretty manageable example. So the next module deals with Lagrange duality again, however, in that case, only as applied to linear programming problems or linearly constrained optimization problems. So we'll have an opportunity to expand upon some of the lessons we learned in module number 4 in this module, as well as learn how those can specifically be applied to linear problems.